Hello, everyone. Welcome to lecture 22. This is going to take the place of our normal class that we won't be having in recognition of Holy Week. This will be a review for exam 3. Okay, so the goal is I'm just going to be going through some slides that I think highlight some key points from this unit that will hopefully be helpful in your review. And so one of the key concepts that we covered to start chapter 14 was Bronsted-Lowry acids and bases. It's of course important to know this. One of the key concepts that you'll be expected to know for the exam is what is a conjugate acid, what is a conjugate base, in addition to, of course, what is a conjugate acid-base pair. So for example, in this bottom reaction here, we have water reacting with ammonia. Water is going to be our acid forming the conjugate base hydroxide. NH3 is going to be our base, which accepts a proton to form a conjugate acid. So an acid and a base would always be on the reactant side. A conjugate acid, conjugate base will always be on the products side, right? Another important definition, of course, is pH and its corollary pOH. So if you are able to determine the concentration of hydronium, which is this H3O+, in a solution, the pH is just the negative log of that concentration, right? If you if you want to solve for the concentration of hydronium and you have the pH, you simply do 10 to the negative pH is equal to your concentration of hydronium, okay? pOH is just the inverse of that, explained here. And then a reminder that Kw is equal to the concentration of H3O+ times the concentration of hydroxide that are present in the solution. And Kw will always equal 1.0 times 10 to the negative 14th. And in neutral water, of course, our concentration of H3O+ and OH- will be equal. And if we were to do pKw, that is equal to pKa, or pardon me, pH plus pOH. And again, that's equal to a value of 14. Okay, so you should know and understand how to convert between all of these different species. Okay. Probably the only thing I suggest that you memorize and just definitely know are the strong acids and strong bases that are listed here. So these are species that will totally dissociate when dissolved in water. So our strong acids are HCl, HBr, HI, HNO3, which is nitric acid, HClO4, perchloric acid, and H2SO4, which is sulfuric acid. Our strong bases are things that are in the first row of the periodic table, or so lithium, sodium, potassium, and they're hydroxides. And then the second column of the periodic table, calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay, and so if something is a strong acid or strong base, it will fully dissociate. That would mean that for our strong acids, the conjugate bases, so for example, chloride or iodide or nitrate or perchlorate, that would mean that those conjugate acids, or conjugate bases rather, do not react with water. So say we had sodium perchlorate, that would not have any effect on the pH because we know that perchlorate is the weakest of weak conjugate bases, and so it would not react with water to alter the pH of a solution, right? Anything that is not a strong acid or a strong base, you can assume would be a weak acid or base that would partially ionize in water. So for example, basically, or I should say, a way to kind of characterize this, anything that is positively charged will typically act more as an acid. Anything that is negatively charged will generally act as a base. Of course, there are exceptions to that. And of course, neutral complexes such as water can be amphoteric, meaning they react with both, or can react as both an acid or a base. But generally speaking, that is something to keep in mind. Okay. Another thing that you may be asked to calculate on the exam is percent ionization. So this is just the concentration of the hydroxide or the hydroxide or the hydronium at equilibrium divided by the initial concentration of the acid or base times 100. So pretty easy formula to remember, just coming up with a fraction and then multiplying it by 100, right? One thing that I know is tricky for a lot of people to understand is how different salts dissolve and affect pH. So this was an example where we have ammonium chloride. And so the first step is just thinking about how a solid would dissolve and what ions it would form. So when NH4 ammonium chloride dissolves, it forms ammonium, NH4 plus, chloride minus. We know that ammonium is a weak acid, and so it would react with water to form hydronium and the conjugate base, ammonia, right? We know that NH3 is one of our weak bases. In this case, it would be the conjugate base, right? Chloride, we know, on the other hand, would not have any effect on the pH, like I discussed earlier, because chloride is the conjugate base of a strong acid, which is HCl. So that means that this reaction does not occur, or we could also say that this reaction just totally favors the reactants, right? We could do the same thing for a basic species. So we have sodium acetate here. And so sodium acetate dissolves into sodium and acetate. The acetate would react with water to form a more basic solution because acetate is a base, would form the conjugate acid, acetic acid, right? Sodium is the conjugate acid of a weak base, or a strong base rather, sodium hydroxide. So we would say that the reaction is entirely favoring the reactants. If sodium were to react with water, we could also just say sodium does not react with water. Okay. Polyprotic acids may also appear on the exam. The main thing to know for polyprotic acids is that they can dissociate multiple times, but for the purposes of general chemistry, the only thing you need to consider is Ka1. And so an example we would give, you would just calculate, for example, the concentration of hydronium in water using a normal ice chart, and you would only use Ka1 for that dissociation. Okay. Right, continuing on, one of the other ways that the pH of water can be affected is if there is a strong or a highly charged metal species. So if we have any metal ions that are 3+, so a classic example is aluminum 3+, when they bind to water, that water will actually become acidic and we will form metal hydroxides and produce hydronium. So another way that the pH of pure water can be altered is through the addition of strongly cationic, so again, having a charge of 3+ or greater, a metal ion that will make the solution acidic. Okay. This is something that may come up as well, just periodic trends in acid strengths. So a reminder that the two things that affect the relative acid strength is how electronegative an anion is, with things that are more electronegative leading to stronger bonds, balanced with also considering, or a stronger acid rather, not a stronger bond, because we have a more polar bond. And then things can be balanced by considering atomic size as well. So our strongest acids on this portion of the periodic table are HCl, HBr, HI, because chloride, bromide, iodide are all quite electronegative as well as quite large. That's why those are the strongest. Whereas if we consider something like HF, fluorine is obviously very electronegative, but it's also quite small, meaning that we would have a stronger bond, making HF a weak acid instead of a strong acid. Okay. Another thing, just a quick reminder, oxyacids. So in oxyacids, the more oxygens you have, the stronger the acid will be. This is pretty neatly illustrated by this graphic here, where as we add in more and more oxygens, our acid gets stronger and stronger, right? Right, next up we have buffers. So in a buffer, we essentially have a mixture of a weak acid and a conjugate base. you can only form buffers with weak acids and conjugate bases. You can't form them with strong acids or bases. That becomes important. Basically, we can't form buffers with a pH of 1, for example, and that's because in those sorts of situations, we no longer have a weak acid. Any acid that has a pH of 1 would then be considered a strong acid if it dissociates that much, right? And so the thing about buffers is they are resistant to changes in pH. If we started with an equal amount of both our acid species, in this case acetic acid, and our basic species, which is acetate in this example, then we could add either acid or base, and it would change the relative concentrations between the two. But as long as we don't exceed our buffering capacity, there would only be a minimal change in the pH, which is, of course, due to the use of our Henderson-Hasselbalch equation. So don't worry as much about buffer efficiency, but anytime you read the word buffer, you should think to yourself, buffer, use Henderson-Hasselbalch. And that's this equation here, where pH is equal to the pKa plus the log of base over acid. And so that is a definite key equation to know, and it is ultimately derived from the equilibrium. And so someone I know asked when do we use BCA charts and when do we use an ice chart or a Henderson-Hasselbalch chart? So the key to remember there is that you use a BCA chart anytime you have a buffer or a weak acid or a weak base. And the key is that you add in some sort of strong acid or strong base. And so with our BCA charts, a reminder that the reaction arrow always goes all the way to products for BCA charts. And so that is because we are adding a strong acid or a strong base that is reacting with weak acid or weak base. Okay, BCA charts should also be calculated in moles as a reminder. If you still have both conjugate acid and weak acid and conjugate base present after the addition of a strong acid or a strong base, then you can use the Henderson-Hasselbalch equation in order to solve for your pH. If you only have weak acid or strong base, or weak acid or conjugate base left over, then you have to use an ice chart in order to solve for the pH. Okay. All right, that takes us to titrations. And so in this example, this is a strong acid and a strong base titrated with each other. And so just a reminder, if we titrate a strong acid and a strong base, our equivalence point pH will be 7.0, and we will have a very steep curve. Okay, and so prior to essentially this very steep curve, well, basically prior to the equivalence point, it will just determine how much acid we started with. After the equivalence point, it will determine how much base that we have added. Okay? With a weak acid and a weak acid being titrated by a strong base, in that case, our equivalence point is going to be greater than 7, be basic. That is because at the point where we have added the same number of moles of NaOH that we started with of weak acid, at that point, all that would be left is A minus, or sodium A, we could say, where A is just a generic conjugate base there. And at that point, that conjugate base will react with water in order to form a basic solution, right? Once you get past the steep part of the curve, though, your pH will ultimately be determined by the excess hydroxide that you have added. Okay. All right. We also, of course, have a weak base titrated with a strong acid. I will say, whether you're starting with a weak acid or a weak base, we will always add strong acid or strong base. So in this case, we're starting with a weak base, adding strong acid. The reverse is true then. So at our equivalence point, our pH would be less than 7 because at our equivalence point, all we would have left is ammonium. And so ammonium could react with water in order to form an hydronium, which makes the solution acidic. Okay. All right, that concludes chapter 14. So on to chapter 15. The key concepts for chapter 15 is that we are dealing with solubility equilibria. So any salt that has a KSP value is a salt that is sparingly soluble. And so, oh, noticing a typo there. I put sprainingly. I don't even think that's a word. Anyhow, um, for these salts, or for these sorts of equilibrium equations, they'll always follow the same formula of starting with a solid as our reactant, and then that solid will dissolve to form the two component ions on the product side. Then our KSP equation is always going to be products over reactants. Our products are our dissolved ions. In this case, and all cases of KSP, our reactant is just a solid. We do not include solids in equilibrium expressions, and so this would be our final KSP expression. Okay. Right, and so in generic terms, again, we have start with some sort of salt. It will dissolve and form dissolved species. Those dissolved species will have some amount of charge, and depending on the stoichiometric coefficients in front of our dissolved ions, those will be turned into exponents in the KSP expression. Okay. Next up, we have Lewis acids and bases. So a reminder that a Lewis acid is something that will accept an electron pair, whereas a Lewis base will donate an electron pair. So in this example, we have aluminum trichloride. It does not have any lone pairs on the aluminum. Our ammonia, our NH3, does have a lone pair that can donate into those aluminum orbitals and form a bond. And so we would call this aluminum a Lewis acid, we'd call this NH3 a Lewis base. What they form when they come together is just a Lewis acid base pair. So it's not the most creative name, but it is at least descriptive. A reminder that some of the key identifiers for from class are Lewis bases are typically metals with a positive charge. So any sort of metal with a positive charge, metals in general tend to be Lewis acids. And then Lewis bases, or pardon me, the other form of Lewis acid that we also identify often is compounds containing boron. So if it has boron, it is probably a Lewis acid. Okay. For Lewis bases, it can be anything with a lone pair. And so in this second example, our Lewis acid is our BCl3. Again, compounds with boron tend to be Lewis acids. Our Lewis base is this organic compound called diethyl ether that has lone pairs. And so the lone pair donates into the BCl3, and we get a Lewis acid base complex as our product. Right, so in addition to KSP, we also have KF. So KF is what happens when we form coordination complexes that we can also call complex ions. Typically, you have some sort of metal ion and then ligand. So in this case, our ligand is ammonia, NH3. And when they react, the key identifier of a complex ion is something that is charged. So because it is charged, it will be soluble. And so it will be AgNH3 2+. Okay. And our formation constant, like all of our equilibrium constants, is just products over reactants. And so we have our product there and put it over our reactants, and it has, of course, some value. Typically, these KF values tend to be quite large, so 1.7 times 10 to the 7th, quite a bit larger than what we're used to working with for other equilibria. Okay, we can add KSP expressions and KF expressions together. So when we do that, say we have silver chloride, when we add in the presence of ammonia, NH3, we can form the complex ion, which is this silver amine plus, and then our overall reaction constant can be calculated by just multiplying our two K values together. So KSP times KF is equal to our new K value of 2.73 times 10 to the minus third. Okay. Right, and then finally, we would consider the effect of pH on solubility as well. So if you have a salt that is partially soluble, for this example, calcium fluoride, we would want to see or be able to identify that calcium is the conjugate acid of a strong base, so that will not have any effect on the pH. But fluoride is the conjugate base of a weak acid, HF, right? And so because of that, calcium fluoride would more easily dissolve in acidic solution because that fluoride could react with our excess hydronium that would be present in an acidic solution to form HF and water, of course. Okay. You won't have to be responsible for calculating an equilibrium constant. Things get very complicated very quickly when we include acid-base equilibria with KSP equilibria, so you don't need to worry about that, but it can be done. Okay, I think that's it for me. Good luck studying. If you have any questions, please feel free to let me know in office hours or drop me an email. Take care, everyone.